Welcome back. We're in the middle of translating logical expressions into programs so that we can move data around in a way that makes sense to how we think about our information. How can I make sure that what I designed today might be used again tomorrow? One of the strategies is to use what's called a universal program. How do we make a universal program? What would it even mean to anticipate the future? Let's imagine that the logical operators that we're interested in promoting into programs are logic that people will use now and into the future, such as and, ors, implies, for alls exists, modal logic, whatever you think of. Logic has been quite resilient for thousands of years. It's reasonable to think it'll be used for a few more. Once you have a logical operator in mind, we know how to convert that into a data type. But now I want to point out that sometimes these data types have a very special property. The kind of logic that they might imply could be universal, meaning it's something that once programmed properly cannot be improved upon. Let's go back to our video on the comic of commutative diagrams. That's simply a way to try to draw diagrams that can help us relate our ideas to other sciences, other people, and they might help us compute, because what they're doing is they're hiding equations in disguise. So I want to use a comic book style, where each frame takes a moment in time and progresses over the space. As we do this, we'll draw less and less pictures and just put in formal symbols. But you'll remember the architecture of the story was the following. There once was a boy that had strings and integers. These are playful ways to remember data types in real life. Strings of characters and integers, numbers you might put in a computer. We have a domino for the integers and a pool of string for the strings. That was the given information. And what we're going to do with our universal programs is we're going to start with some given information. It might be different from time to time, but we'll put that in the first box. Next in our story is some progression. In this case, what we were told to do was to combine these data into one piece of data. Here it was a pile on the rug. The key idea was that our son took this information and was able to extract out the string and the integer. You can now start to see that these are examples of elimination rules. We've created a data type and we're able to get information out of it. What we haven't done in this diagram is indicate how we're going to create examples of this. We don't have an introduction rule yet. And this is the part where we can start to think ahead towards a universal program. While we already know how to introduce things based on the theory of and, we're now going to augment our and we're going to, in the process, discover that there is a closer relationship between our new and the or. If you remember our previous video, we drew out the distinction between and or. Or needed to depend on many more data points than and seemed to. It was this disjunctive dilemma that caused trouble in comparing the two. Today we fix that. So let's see what it would take to introduce data. Introduction means the data ends up in the pile, meaning if this is our new data type, we want a way to describe how to add things to it. In this case, we would need an arrow that ends in the pile. Notice there is no such arrow. Where we're going to get it is by looking at a challenger. In our story, we came along and the challenger was the dad. The dad walked into the room and said, "Why are you organizing it this way? Here's an alternative way to organize it," suggesting a chest of drawers where we put strings in the top drawer and integers, dominoes, in the bottom drawer. There's nothing wrong with that approach. It's simply an alternative. What we see is that there are still two elimination rules for this alternative challenger. So now we have two data types. One is our son's data type, the very first one that just put them in the pile in the middle, and the other one was the dad's solution, the sterile put them in drawers. Our original hero, the son, gets to beat the dad. How does he beat the dad? What he shows is that everything that the dad could do could be reproduced by the son. The key idea is every example the dad creates could be turned into inputs over here. For example, you could empty the drawers and pile them in the middle. That's a proof that the son's approach can take data in from any challenger. This is the key idea to making a universal program. When you make a universal program, you first describe what the data type is that you're going to create, along with perhaps introductions or elimination rules, but you may not have the whole story yet. In this story, we had just part of it. We just took the elimination rules. Once we had the elimination rules, we took any other challenger with identical eliminations. They too could provide some of this information. Maybe they can do it as well as us, maybe they can do it better than us, maybe they can't do it as good as us. To be a universal program, however, it would be enough to show that anything they can do, we can do at least as well. And here, by taking the drawers out and dumping them in the pile, we recognize that anything that could have been done with the drawers could also have been done with the piles. So there's an arrow taking this one solution, the challenger solution, to the sun solution. Why does this win? Well, it goes back to our equational view of commutative diagrams. If we start here, we could open the drawer, pick out a spool of thread, and set that string down. Or we could first dump it in the pile and then later select that thread. They go to the same result. If we don't care about when in time they happen and where they might move in between, the result is their string. Likewise, we could take the bottom drawer and pull out a domino. Or we could just dump the domino in the pile and then later find the domino and put it out. Now you might start to realize that there's advantages to the top one that might not be in the bottom one, such as the speed. Here it's organized in a way that I can quickly find it. But if I just make a heap, it's still technically there. There's nothing incorrect about that data type. The key observation we're doing is that we're focusing purely on the logic we decided to expose. If we are not exposing resources, then all we can say is, can you get the data out? And this solution, the pile on the floor, is in fact universal for the goals of combining strings and integers. It may not be universal if we take into account resources, and that's when we can start to tease apart better programs. Nevertheless, the takeaway message is this. A great design of a program is one that won't have to be improved in the future. It already folds in a mechanism to take anyone else's approach and translate it into the one we're using. This makes it survive into the future. Now, of course, individual programming languages may come and go, but the philosophy, the design of the architecture is what's universal. If we write this in sequent calculus, we can in principle compile that to any future program. It'll always behave according to the logic we want and doesn't need any updates. Now, given that this is our new view of AND, let's do this with some more technical notation. Let's put in types and arrows as functions and see the process through all the way. I've now erased the cartoons and put in placeholders for arbitrary data types. We're starting to take this exercise more seriously. A could be integers and strings still, but the point is now they are arbitrary data types. Our first goal in creating an AND metaphor was the Cartesian pair, putting A comma B's together. That's what we'll now put in the middle. And with that, we label the arrows by the elimination rules. They're elimination because the data type we created has arrows coming out of it. We're removing data from it. We are eliminating the original pair type. Having created these elimination rules, I'm now ready to move on to the challenger. The challenger is an unknown data type. Somebody comes in with a different solution, maybe better than ours. We now have to compete with their challenge. So here's our challenger. Notice that our challenger does the very same thing that we've done in our first square. They match it symbol for symbol, arrow for arrow. Here, we only went as far as getting the elimination rules out of our characterization of this type. Therefore, the challenger will have to provide its own elimination rules. They might be called different things. After all, we don't know how C is organized. We simply know how we organized our own data type. But in order to compare techniques, we need to have elimination rules that we can compare one to one. For every elimination rule out of AB, there needs to be an elimination rule corresponding out of C, the challenger's approach. Now, what would it mean to have won in a battle against a challenger? It should mean that everything they do, we can imitate. Better yet, how about if everything they do can be converted to an example of the data we have? Therefore, we wouldn't even need to call their elimination rules, we would call our own. So here we have it. From our challenger's view of elimination rules and our own elimination rules, we win whenever we can transform their data into our kind of data. Once we do that transformation, we can use our own elimination rules to do whatever we want. That's the survival of our method over somebody else's. If anyone else comes along to challenge us, the same mechanism will translate their challenge into one of our pieces of data. Notice it could be a different introduction rule. If a new challenger comes along, they will have their own elimination rules heading to A and B. Our job is not to make one introduction rule from C and D. That's not even possible. These are different starting points. It'll need a new arrow. Here, we simply take D and map an arrow to A comma B. If we can show that no matter how somebody creates a challenge for us, as in this picture, here, somewhere else, if we can always convert their challenge from their given elimination rules into a map from their data type to ours, then our data type is robust. It will work now and into the future, because in the future, any new challenger will have its elimination rules. They'll hand them to our internal program, and our program will convert them into introduction rules into A comma B. That's how we know that our design is robust to any future challenges. It's universal. Can it be done? Yes. To see that, let's write some actual terms. Until next time. That's how you take care of a chalkboard.